let's see how we can take first 5 natural numbers as a set. So there are two kinds of forms in which you can actually show a set. So first is the roster form. It is known as the roster or tabular form. It's usually called roster. It's also called tabular form. And second one is the set builder form. These are the two ways of showing a particular set. For example, first 5 natural numbers. So A is a set of first 5 natural numbers. So I'll write A is equal to X. Sorry, A is equal to, and I'll tabulate. I'll enlist all the possible elements. So you will have 1, 2, 3, 4, 5. That is basically your roster form. And in the set builder form, you will actually not write the whole set, all the elements together, but you will actually define an element X, and X is one of the first 5 natural numbers. Is this part clear, what I'm saying? So you can
Yes, sir.
define a set by directly tabulating all the elements of the set, or you can actually write the definition of an element in the set, and that will also define a set. Depending on what kind of set you are using, you can use either one. Sometimes the roster form is better, sometimes the set builder form is better, sometimes both are okay, right?
Okay, sir.
So let's take a very simple example and then we'll move forward.
Sir.
If I say write the set X, X is a positive integer and X square is less than 40. Which form is this? Can you identify? Which
Yes,
form
sir.
is this?
Set builder form.
Very good. It is the set builder form. So you have to write this in the roster form. So what will be
Sure,
the
sir.
roster form? Can you inform me, please?
So any positive integer whose square is greater than 40. So
Less
we would be
than
starting
40.
from
Yes.
less than 40.
So set
So
A, you have to write it properly. So set A equals, and then what are the values?
7, 8, 9, 10, 11, 22.
Less than 40. Varun.
Okay, less than 40. Then
Yes.
it is 1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, and 6. Yes, that is correct. So I think you have understood this. We'll move forward. So the first exercise is based on that. You can actually go through it or you can totally ignore it. It's not a problem if you don't do this exercise, okay? Because it is based on set builder form and roster form. It's not a big deal, okay? You can go through it yourself. Now let's look at some special kind of sets. One is the empty set. As the name suggests, the empty set is a set which has no elements in it. So the number of elements in the empty set is 0. So it can be called as the empty set or null set or void set. So some example, let's take one example. Example is names of persons living on Mars. So how many elements do you think this one will have?
None.
None, right? So another example is, if you want to go a little bit mathematical, you can say a set D is equal to X x square is equal to 4 and x is odd. So that's also not possible because x square equal to 4 means x is either -2 and 2, but it cannot be odd, and hence it has a 0. It has 0 elements, hence
That's
it is a
zero,
null
yes.
set, right? It's a null set.
Yes.
Okay, let's move forward. In the next part, I want to talk about finite and infinite sets. As the name suggests, finite set is one which has finite number of elements. Whereas infinite set has infinite number of elements. And I don't think I need to give you any examples. It is well understood that
Yes, sir.
can have n number of examples. Okay, so I'll just skip forward. Equal sets. Equal sets are sets in which all the elements are exactly same. That is, there should not be a difference of even one element.
Yes, sir.
So example, I can say set A is equal to X. X is one of first 5 whole numbers. And then I can write another set B, and B can be in roster form. So I can write 0, 1, 2, 3, 4. So I can say set A is actually equal to set B, right? So if there is even a difference of a single element, then you will obviously have a there will be unequal sets. Okay, equal sets means it has to be exactly same. Both of the sets, all the elements have to be the same. Next, then there is a bunch of examples and exercise 9.2, which you may 1.2, which you may also sort of ignore. I mean, there's not much here going on. Subsets. What is a subset? Subset means if I draw a Venn diagram, if this whole rectangle is set B, and then you have
Part of it.
a smaller part A, then I can say A is a subset of B.
Okay, sir.
And how do I write it mathematically? I can write A subset B. Okay. Now there are two types of subsets. One is proper subset. Proper subset is this case. Okay. Proper subset means A cannot be equal to B. Then A is a subset of B. This is a proper subset. And an improper subset means that it is possible that A equals B and it is written as A as a subset of B. You see that symbol difference,
Okay.
symbolical difference is there. So it is possible
Yes,
that
sir.
they might be equal. Okay. So if it
Okay,
is a
sir.
proper subset, then it has to be smaller. A
Okay,
is
sir.
smaller than B, essentially. And A can be equal to B. Obviously, two equal sets are subsets of each other, but they are improper subsets. So again, not much going on here.
Yes, sir.
So maybe you can just make a note of natural numbers are subset of integers, which are subsets of rational numbers, and rational
Okay,
numbers
these
are
are like
subsets
the-
of real numbers. Sorry.
So these are like the universal sets, right?
I have not yet talked about universal set. Universal set, which one you're talking about?
Or like what are you giving an example right now?
Yeah, so universal set has to be defined first. Okay.
Okay.
So in this case, if I'm talking about numbers, then a set which entails both real and complex numbers is actually a set which is the universal set, right? So let me define a set A. A equals X. X is a complex number.
Okay, so
When I say complex number, I am automatically taking into account all the real numbers. Am I not?
yes, sir.
Because you
Yes, sir.
know a complex number Z can be defined as A plus iota B. If B goes to 0, it is the real number, right?
Yes,
So
sir.
the universal set in this case will be A, and rest will be all subsets, right? A is the complex number set, and then you have real numbers, then you have rational numbers, then you have integers, and then you have natural numbers. I have not included the whole number in this particular count, but you can actually
Yes,
put
sir.
a W in between N and Z. I'm sure you are aware of that, right?
Yes, sir. Yes, sir.
Now let's talk about the next part, which is a power set. Okay, let's talk about it. Now things are getting a little bit more serious. So let's get down to that. A power set if A is a set, then the collection of all subsets of A is called the power set of A.
Okay, sir. Yeah, got it.
Right? All subsets of A is called the power subset of A. It is known as, it is denoted by PA, right? So let us take a look at what all we can do. Note that number of elements, which is also known as cardinality, N is what? This is basically the number of elements
Elements, yes, sir.
in the power set. N is basically number of elements, or cardinality. Number of
Yes, sir.
elements in power set of A is equal to 2 raised to the power m, where m is number of elements in A, or I can say that n of A is equal to m. This implies n of PA will be 2 to the power m. So I would like you to note this down, that if number of elements in a particular set is m, then number of elements in the power set of that same set is 2 to the power m. Please note this down.
Okay, sir.
Yeah.
Sir, could you give me an example for this?
I am
Sir,
giving,
I'm able to like-
I am going forward with the example of this one. A very small example, just to keep it clear for you. Example, set A is equal to 1 and 2. Then what will be the power set of A? Power set of A is a set which contains all the subsets of A. So can you please name all the subsets of A? What will be the first set? There is no sequence, but I
Okay,
want you to go
first set,
sequentially.
so-
Yes,
It will be like 1 or simpleton set.
1 and 2 and 1, 2. But what about the null set? That is also
Null
part of
set
this.
too? Yes,
So
sir.
5 will be there, then 1 will be there, the set consisting of only 1, then 2 will be there, and obviously the set itself will also be there, and that is the power set of A12, right?
Okay, sir. Yes, sir. Got it.
So we already discussed about universal set. So in a particular context, the largest set which consists of all the subsets is known as the universal set, right?
Sir. Okay. Yes, sir.
Okay. So let me move forward. Yeah, not much in the exercise. So I'm going to go forward. Venn diagrams. So I'm sure you are slightly aware of Venn diagrams already. Let's just explore them. So first of all, we have to define a universal set. The largest rectangle that we draw is the universal set. So the rectangle is the universal set, right? And then
Yes, sir.
you have several other sets inside. So if you
Yes, sir.
have this kind of a set and then another set like this, I can name this set A, this set B. This is A intersection B.
Intersection B. Yes, sir.
Yeah. Okay, so that is basically Venn diagram. We'll talk about more in Venn diagrams. First, we'll talk about operations on sets. So this is where the important part starts to come. So operations on sets is, first of all, we'll talk about union of sets, the union operator. So the union of A and B, which is basically A union B, is the set consisting of all the elements of A and all the elements of B the common elements taken only once. So you don't have to repeat the common elements. They are only taken once. So for example, just a simple example. Let's say A is a set 2, 4, 6, 8, and B is a set 6, 8, 10, 12. Then A union B will obviously 2, 4, B, 2, 4, 6, 8, and 6, 8 should not be repeated. So this
Yes,
will be
sir.
10, 12.
10, 12.
Right?
Yes, sir.
Okay. Another definition of union is union of sets, two sets A and B is the set C, which consists of all those elements which are either in A or in B or in both. So definition wise, I can say A union B is equal to, in the set builder form, I can write X, where X belongs to A or X belongs to B.
Yes, sir.
In terms of Venn diagram, where a universal set exists, I have two sets A and B. Then the shaded portion, let me shade it in a different manner. I have two sets A and B.
Yes, sir.
Then the shaded portions, which involve A and B and the common elements, these are the union set. So C is actually the yellow portion, which includes A, B, and everything which is in both, right? So let's look at some properties of the union operator. So first of all, A union B, and these are very important, so please bear them in mind, is equal to B union A is known as the commutative law.
Yes, sir.
Second, A union B union C is equal to A union B union C. This is known as the associative law. A union phi is equal to A law of identity element. Phi is identity of the union operator. Don't misinterpret this as universal set. This is the union operator.
Yes, sir. Got it.
And A union A is equal to A. It is known as the idempotent law. A union A is
Okay,
A is known as the idempotent law. And universal set union A is the universal set itself, law of universal set. I hope it is clear till here.
Yes, sir. It is.
Okay. Let's go forward. Next is intersection of sets. Intersection of sets A and B is the set of all elements which are common to both A and B. So the symbol that you use is this symbol, which is just the upside down of the union operator. And if you want to see the Venn diagram for this, you will have a union operator, the universal set, and then you'll have A and you have B, and this region in the middle is A intersection B. Is that clear?
Yes, sir.
So another definition is the intersection of two sets A and B is the set of all elements let me just create some space here. Of all elements which belong to both A and B. Symbolically, you can write A intersection B is equal to X, where X belongs to A and X belongs to B. Compare this to X belongs to A or X belongs to B is the union, whereas if you put an and here, that is the intersection.
Intersection. Yes, sir.
So let's look at some properties of the intersection. Some properties of intersection operation. First is A intersection B equals B intersection A. It is known as the commutative law. A intersection B intersection C is equal to A intersection B intersection C. Just like the union operator, you have this is also the associative law. Then phi intersection A is equal to phi, whereas union intersection A is equal to A. These are the law of null set phi and the universal set. Two different laws combined
Okay.
together, right? And then A intersection A is A. It is again known as the idempotent law.
Okay.
And lastly, we have A intersection B. So this is one worth noting. B union C is equal to A intersection B union
Unions.
A intersection C, and this is known as the distributive
Distributive.
law. Yes. Maybe you can just mark this one as important,
Yes, sir.
and then we'll move forward. Now let's look at another concept, difference of sets. Difference of sets A and B in this order, that is A minus B, because order matters in subtraction. So A minus B is the set of elements which belong to A but not to B, right? So you can write, I think it is easy to write that A minus B is equal to X. X belongs to A, but X does not belong to B. Clear?
Okay, sir.
Right. Note here that disjoint sets are sets whose intersection is the null set. That is, they do not intersect. So another thing to note here is that A minus B, A intersection B, and B minus A are mutually disjoint sets. That is, if you take any two, you will actually get no intersection between them, right?
Yes, sir.
Okay. Let me find some good questions for you. Let us do an example. Yes. So let's look at another concept, which is slightly more complicated.
Okay, sir.
Complement of a set. If U is the universal set and A is a subset of U, then the complement of A is the set of all elements of U which are not elements of A. Right? So anything which is not part of A but is part of the universal set is known as the complement of set A. So symbolically, I can write complement of A is A prime or A dash A prime is equal to X, where X belongs to U, the universal set, and X does not belong to A. Right?
Okay, sir.
You can also say that A prime is basically universal set minus A.
Okay, sir.
Right? That way also you can write. So let's look at some examples.
Sir.
These properties are quite important. Let's take a look at them.
Yeah,
First
sure.
one is the complement laws. Complement laws are A union A prime is equal to universal set, of course, and A intersection A prime is equal to phi, obviously. Second one is the De Morgan's law, which we just verified in the past question. De Morgan's law is A union B in complement is equal to A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. So this one you can mark as important. Third one, law of double complementation. Double complementation means A prime prime will be A. So complement of A, complement of the complement of A is A itself.
Sir.
Law of empty set and universal set.
Ah,
Phi prime is equal to U
yes.
and U prime is equal to phi. Practical problems. On union and the section of sets. Before we go to the practical problems, we must know a few formulae. Let's take a look at them.
Yes, sir.
Number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Right?
Yes. Yes.
Then number of elements in A union B union C is equal to n of A plus n of B plus n of C minus n A intersection B minus n B intersection C minus n A intersection C plus n A intersection B intersection C. This is an important part.
Ah,
So these are the two examples I wanted you to see.
okay, sir.
Now let's look at a few examples. Okay.